yeah, I'll start recording this. The homework is due today at noon, but that's a little bit soft. You just need to get it to me so that I can, finish up before I've got to do grades. Some of you are missing a couple of homeworks. If you're watching this recording, be sure to get those to me as soon as you can, or you might be disappointed. See what I did there? Okay, any questions? All right, so what I'm going to do is I'm going to talk kind of about some fun stuff today. And as I said, this might be construed as sort of an advertisement, if you will, for doing a topics course in the fall. And so what I want to talk about today is there are people out there that do research in some of these other areas that I call scientific domains that will probably be offended by this. I apologize for that. So one of the things that I'm interested in is factorization. And when you talk about ring theory, and I'm going to restrict myself, to integral domains for this talk. Although Dan Anderson and some of the students did a lot of good work when it comes to relaxing domains down to ring 0 to 5, but I'm going to stick strictly to domains. Now, when you're talking about rings, you're talking about mathematical structures that have two operations, addition and multiplication. And under addition, it's just an abelian group, right? So the only thing that makes commutative rings, the study of that, any different than abelian groups is the multiplicative structure. Factorization might be construed as what separates out rings from studying just ordinary abelian groups. So let me define the types of domains. Whatever be a domain, we say R is I'm going to go through defining these domains all the time. A UFD if every non-zero non-unit is a product of primes. We've talked about UFD rather extensively, and this is a more mature definition than just talking about it in terms of irreducibles. B, an HFD, or half factorial domain, if our atomic so I'm going to make a definition after this. We define atomic in class. I have it here. Is atomic, and if we have irreducible factorizations, alpha 1, alpha 2, alpha n, beta 1, beta 2, beta m. So we've got equal length. C, a finite factorization domain. FFD if R is atomic and So I've mentioned atomic twice. Let me remind you, atomic means every non-zero non-unit factor into irreducibles. And every non-zero non-unit has only finitely many factorizations. Up to associates. So I don't count when you tweak things by units. This is actually equivalent to saying it's atomic, and every non-zero non-unit is divisible by only finitely many different irreducibles up to associates. This one's real VFD. A bounded factorization domain is atomic, and each non-zero non-unit has a bound on the length of its irreducible factorizations. Might have a lot of factorizations actually, but there's a bound on the length. Right, like this element has no more, any irreducible factorization has no more than 20 irreducible factors. ACCP means the ascending chain condition on principal ideals. This is like Noetherian, right? Noetherian has the ascending chain condition on ideals. This is a little bit weaker than this. This may not satisfy the ascending chain condition on all ideals, but it might satisfy the ascending chain condition on principal ideals. A1, A2, A3, and chain like this, count the chain, stabilizes. Now, in a very famous paper, so I wouldn't say all the content, but a lot of the content of this paper by Dan Anderson, David Anderson, and Mohamed Sprula in 1990. Actually, rather sadly, in the last 8 months, 2 out of 3 of those letters actually passed away. But they wrote a very famous paper now, and this kind of famous diagram is from it. So for these factorization types, we have these change implications. Now, the proof that most of these implications work is not difficult. In fact, the fact that you're a unique factorization domain clearly implies that you're a half factorial domain and a finite factorization domain, because actually these are the best finite factorization domains because any non-zero non-unit has only one factorization, right? The fact that if you've got finitely many factorizations that you've got a bound on the lengths is clear. What's probably a little bit less clear is bounded gives you ACCP, and neither of these proofs are terribly difficult, but there's something to show. It doesn't immediately fall from the definition like some of the other connections. So proving this chain, proving that all these arrows work is not too bad. The interesting part is actually showing that none of the arrows can be reversed, right? So there's kind of a wealth of examples in these papers. Some of them already known that show that these don't reverse in general. Let me just take some examples. I'll probably go through details here. Here, okay, we've seen these are, for example, HFDs that are not UFDs. These are all examples of HFDs, and I think we kind of saw it. Oh, and this can also be power series as well as just polynomials. Example, if R is a ring of integers, a ring of algebraic integers, so the integral closure of Z and some finite field, then R is always an F. You can actually use some number theory yin yang for this, because there's some results in number theory that say if you've got an element of a certain norm and there's only finite many elements that divide it, kind of thing, and that gives you the any element ring of integers actually has only finite many different irreducibles dividing it, so you get FFD. I can use the fact that this is a ring of algebraic integers to trifurcate in a certain sense. If CLR 1, then R is UFD. If CLR is 2, then R is HFD, but not UFD. Right, that's the Carlos theorem. And if the order of the class group is bigger than 2, then R is FFD, but not HFD. Now, there are others here, but here's kind of an interesting. So here's the question. Tom. Anybody know of an example? Okay, and in fact, why are these even not equivalent, right? Because what does it mean to be atomic? It means you take everything and you can factor it, right? So take an element A, break it down, and then maybe breaks down part of the. Doesn't that mean that if you have a chain of ideals, take this element that you want to factor, it's got some factor here, and now that's got some factor here, doesn't that have to terminate?
In this case, the atomic would be more like the actinian condition, right? And ACCP is more like the Invariant condition. So.
Well, I don't know. That's an interesting analog, but I don't know if it spreads that much. So here's what I like to say: ACCP is atomic for idiots, right? In the following sense, start with an element, right, that's not a unit, right? Well, pull off a factor of it, right? So now you've broken it down into two things. Take each of those factors and break those down, right? Because of this ascending chain condition, this process must stop, right? It has to stop, right? Take an element, break it into two things, and take those two elements, break it into two things, follow all those little paths, and they all eventually must terminate, correct? So in other words, if you just naively take something, just start factoring it at random, you're eventually going to reach a place where it factors into irreducibles. That's why I call it atomic gradients. The problem with atomic is atomic just says, hey, I can factor this thing into irreducibles. But if you aren't careful about the way you factor it, you might end up following your path forever, right? So ACCP works no matter what. You take something, you break it up however you want, it breaks up however you want. Eventually, all those paths have to stop. Atomic, there is a way to make it stop, but if you don't follow the right paths, it might go on forever. Now, if you think that this is a little obscure, don't be embarrassed about it, because for many, many years, these two conditions were considered the same. In fact, it was implicit in the literature for a number of years that atomic meant that eventually stopped. And one of my sort of personal heroes, Anne Graham, she wrote a couple of papers. She didn't write a lot of papers, but when she wrote a paper, you should pay attention. She came up with an interesting example. But this is going to lead me down a path here. So first side here. Monoids. And this is going to help me see how things go. What is a monoid? How many of you are familiar with that word? I use it all the time. A monoid is just sort of like a group that's missing its inverses in a certain sense, right? It's closed under addition, and of course, I'm going to talk about commuted monoids. It's closed under addition, and it's got an identity, but perhaps some of the things, or maybe all of the things except for zero, don't have an invert. So, factorization of monoids. Right? Because when you talk about many factorization conditions, you say to yourself, well, you know, really all I'm worried about now at this point is the structure of the multiplicative structure, which is really a monoid because you've got an identity in our range, right? That functions as the multiplicative identity. And you've got irreducible elements, which are going to be sort of irreducible. You can't break them down further than monoids. But you may not have inverses, right? So for example, if you start factoring Z, things like 2 and 3 don't have inverses. Let me give you an example. And so oftentimes when I talk about factorization in monoids, I'm going to talk about additive factorization. Here's my favorite example. This is one of the best examples, I think, to illustrate factorization of monoid. Just take the natural numbers, throw in 0 and jerk out 1. Right? Now, here, instead of writing things multiplicatively, I write them additively. So 0 is a unit, right? Because its inverse is itself, additive. Notice that 2 cannot be broken down, can't be decayed into the sum of any smaller elements. Neither can 3. So the irreducible elements are 2 and 3. Notice every larger element is a linear combination of the naturals 2 and 3. So for example, 4 is 2 plus 2. So we say 4 factors into, it's sort of like 2 squared. Actually it is. Coincidence. Notice 5 is 2 plus 3. Right, so that's the factorization of 5. This irreducible, this irreducible. 6 is interesting because it's 2 plus 2 plus 2. So it's 3 irreducibles this way, and 3 plus 3, right? The analog that I like to think of is you might consider Actually, minus one, you know, it's called this mono, you know. And this is sort of an analog. This is the way that we sort of think of the monoid. Transferring to domains. This is all polynomials, if you will. And notice that the analog of 6 is 2 plus 2 plus 2, which is 3 plus 3. Okay. So we've got kind of the additive analog. This is how you carry it over to a multiplicative situation. Right? Notice though that the factorization, notice this is much more complicated, isn't it? Because this has extra irreducibles. The only irreducibles in the monoid are 2 and 3. But for example, 1 plus x squared is also irreducible here, and there's no analog. Let us try to separate out atomic and ACCP. But M being submonoid of Q generated by play. In So look at the submonoid of Q that's generated by this, and when I say generated by, I mean zeros in there too. Generated by 1/6, 1/20th, 1/42nd, 1/1/6, etc. So in general, 1/2 to the n times the n dot. In the sense of factorization in monoids, it turns out that M is an atomic monoid. The generators are atoms. In fact, you can show that in this monoid, none of these elements can be decomposed into smaller elements that are still in monoid. The fact that Graham's stuck on these different odd primes really helps your case, right? But it's not difficult to show that these things are all atoms. And if you have a monoid that's generated by atoms, it has to be atomic because everything will be a sum of atoms other than zero, right? But it is not ACCP. Anybody see why? So let me do this rather dramatically. This thing is a monoid, right? So when you add this self to it, when you add this thing to itself 3 times, it's still a monoid, right? So 1/2 is a monoid. This is in the monoid. So when you add this to itself 5 times, it's still a monoid. This is in the monoid, so when you add it to itself 7 times, it's in the monoid. Terribly clever, I think. So even though everything in here is can be written as a finite sum of these atoms, it does have an ascending chain. And this is your problem, right? Notice, and this is what I mean about being sloppy, right, and being not careful. 1/2 is can certainly be written as a sum of atoms. Namely, 1/2 is this atom plus this atom plus this atom. But if you're sloppy and say, well, 1/2 is 1/4 plus 1/4, yes, 1/4 can be written as some atoms this way, but if you're not careful and keep going this way, it never stops, right? At any point here, you can stop and write this is a product of that, or a sum of atoms. This is this plus this plus this 7 times, right? But if you're not careful about the way you keep breaking it down, the process may never terminate. It's a subtle difference. Well, this is for monoids. Yeah, this is for monoids, but if you look, it turns out that there's some proving to be done. But if you take this monoid as the possible exponent, so again, this construction, what this looks like is this is polynomials with the variable x, except it's more general because now I'm allowing the exponents to be taken from this crazy monoid. And it turns out this thing is also atomic, but it's not ACCP. Okay. That is sidekick number 1, and I'm gonna kind of finish off that at the end here. Sidekick 2. And I'll give you an open problem with this one too. I'll challenge you, and I suspect that you might think that you're going to go home and sit down in front of Gilligan's Island and scratch the silent paper because it is seductively looks easy. However, it is not. Solve my open problem for you, and if you come be my student and solve a problem with my name on the paper, I'll take your exams for you. Okay, you'll get through with this one. Has anybody heard of Davenport constant? Okay, you've heard of so let G the finite abelian group. And you'll see pretty quickly why I want finite and abelian. And it looks like I've kind of freaked out and had a stroke here because I'm talking about abelian groups and it's not clear what the connection is. Well, I'll make one. Let G be a finite abelian group. We say the sequence of elements of G possible repetition so G1, G2, G K is a 0 sequence. If when you add them up, it's equal. Right? That's what we call a 0 sequence. More generally, the sequence G1, G2, Gk has a 0 subsequence. If there exists I1, 2, m such that G1, G2, Okay, that's really what it means. The zero subsequence is just some subset of that. That's some non-empty subset. So for example, if you have a zero sequence, it certainly has a zero subsequence, right? Because the whole thing's up to zero, so you can just take that subset, or it might even have a smaller zero subsequence. So for example, I won't put my bars up there. That is a zero. That is a zero sequence right there. It's Z4. But it has no proper zero subsequence. If you look at 1, 2, 3, this has zero subsequence. So this sequence right here is not a zero sequence because it actually has a 2, mod 4. However, certainly 1 and 3 have 0, so it's got zero subsequence. It is amazing how important this comes out to be. Let me give you the definition of Davenport constant. Where have you seen this? Like a number theory class? Okay, just in your travels kind of thing. Gotcha.
Yeah,
it really did have a
it's
stroke.
your fault.
Yeah, it's my fault, definitely. But G, I'm gonna give you sort of two companion definitions, if you will, or equivalent. Let G be a finite Billy group. We define Davenport constant of G to be DG. And this is equal to minimum overall n, such that every collection of n elements of G has a zero substance. And let me say that this collection of elements might have repetition. So if you have just n arbitrary elements, they might all be the same, or just any hodgepodge that you have, you're guaranteed that in that collection of n elements, you can pick out some subsequence that actually has zero. And of course, this definition here, it's pretty easy to see why you want to finite here. Equivalently, DG is maximal range of a zero sequence that has no problem. Zero subsequence. So it'll be convenient to think of it both. So from one point of view, it's the smallest n such that any collection of n elements is guaranteed to have a zero subsequence. Or another way to think of it, it's the longest zero sequence you can build that has no proper subsequence. And it's that characterization that's going to help us out here. So let me give you some examples. And I'll let you kind of play around with this. These are all, I'm going to give you a bunch of small examples and they're easy to verify. Anybody want to guess what Davenport constant of Z4 is? How about I won't take a stab at that one. Try 1 0, 0 1, and 1 1. That's a 0. So it's got to be at least, and you can kind of play around with it. See that it's it can be no more than 3. How about Davenport constant C6 is 6, and there's a reason for that. We'll see that in a moment. The Davenport constant of C2, correct sum T4 is actually 5. And the Davenport constant of 3 copies of C2 well, let's see. 1 0 0, 0 1 0, 0 0 1, 1 1 1. And it turns out that that is an example of a maximum. So play around with that just for fun. Let me give you a proposition here that'll sort of clear up the mystery. And then I'll kind of take you almost to the frontiers of what's really known. It's funny because the Davenport constant, people that worked on Davenport constant for many years, this actually grew sort of separately out of 2 pies. One of them, people that like looking at combinatorial group theory kind of thing, just as an exercise. Another group of people got excited about this, did this when there are connections to factorization, which is like, what's it's got to do with anything? We'll see in a moment. Proposition. Let G be abelian and your G n, then Davenport constant G is less than or equal to 1. That's an important theorem because if I have an abelian group of 1 or 200, the Davenport constant could be kind of strange and all this, but it's no more than your group. And the proof of this is really kind of nifty. Select any G1, G2, Gn, and G. And recall, of course, the order of G is exactly n. So pick any of these, possibly with repetition. And let me kind of make a chart. Okay, so make this kind of little triangular staircase here. Now, let me point out that there are exactly n elements here, which is the same as the number of elements in G. Right? If all xi's are distinct, one of them must be 0, right? Because there's n elements of G, one of which is 0. Therefore, on the other hand, suppose 2 of them If not, then two of them, say xi and xj are equal. Right, so if there's some repetition, you get in almost the group, then two of them must be equal. Say these two are. Xi equals xj. Therefore, G1 Gi is Gi plus 1 is Gj. G1 plus G2 plus Gj. And J is the big one. This should just go to I. Okay. This is xj and this is xi. So subtract these offending G1 to Gi off both sides, and you get Gi plus 1 plus Gi plus 2 plus Gj, Gj is equal to 0. So again, Davenport constant plus 1. Beyond that, there's a couple of other theorems. Let me give you two in tandem. These two theorems indicate that there's probably a formula for this. That's what they would sort of seem to be trying to tell you. Let P be prime. Then, and let's say G So basically, this is the case where G is the P group, right? You've got a single prime here. Then the Davenport constant of G is equal to -1. Yeah. And P right? So it's whatever the order, this is -1 or this -1 all the way up, and then add 1, right? And this is the pattern that we saw with Z2, Z2, and Z2, Z2, Z2. Also, so this basically takes care of it for P groups here. But M in the integers with M guiding in, let's say non-zero integers. Then the Davenport constant of Cn, direct sum Cn, is M plus N minus 1. And let me point out that this is the same formula, because this can be written as 1 plus N minus 1 plus N minus 1. Right, so the pattern I think is clear in these last two theorems. You just take the direct summing parts, subtract 1 from the order, add them all up, and then tack on 1 for good measure. Okay. The question is, so this last one is sort of an invariant factor, right? So if you remember from the fundamental theorem of finitely generated abelian groups, when you look at the torsion part, you've got these invariant factors like this, right? You can always write this as a direct sum of cyclic groups where you can order from by dividing. So this is the two invariant factors case. By the way, of course, this is also true for the cyclic case, right? Because Zm, the order of this is n minus 1 plus 1, right? Because notice if you have a cyclic group, the Davenport constant is exactly equal to the order. Because you know that the Davenport constant is less than or equal to the order. But I know it's exactly equal to because all you have to do is just take 1 and add it to itself exactly that many times. And that's a 0 sequence that has no proper subsequence. So this is all very good. So the question is if you have a more general invariant factor case, does this work? So is this equal to mi minus 1, I equals 1 to k, 1, right? And this is what has worked so far. No, k greater than or equal to 4. And I don't think there are any known counterexamples. Right. So that's like even K plus 3 is interesting. I don't think there are any I haven't looked at this problem in a while. I actually haven't really tried to do it, but the smallest known example where this doesn't work is for the case K equals 4 and it's group 1 of 96. Right. And K equals 3 case is I don't think there are any counterexamples that are known at this point. So this is very frustrating. I mean, it is. I've heard people say that they don't think there's any good closed form of the Davenport constant beyond the P group case and the two invariant factor case. Okay. Now, so I look like I freaked out, which sort of steady state, but what is the connection? Why are we talking about this? Well, let me give you follow. So let's start building the connection. There. And suppose that your factor of D is n, so some finite order. If alpha is an irreducible element of D, and the ideal journey about alpha is P1, P2, Pm. Then M is less than or equal to Davenport constant. So if you take the question, so if you take D and take its finite class group, if you find the Davenport constant, which of course for any fixed group you can easily do, of course you can say that you can do with computer theory. Yeah, it's unfortunate I'm using D for Davenport constant, and I'll avoid that in the future. But your M, the number of prime ideals that make up this irreducible principal ideal, is less than or equal to this. And equality holds for some alpha in irreducible state, if there exists infinite many. Actually, and you don't quite need this, but it will work with this, many prime ideas in class. And the reason I use that sort of looser sort of condition is the fact that this will clearly apply to rings of alpha. Okay, so let me give you a theorem here. Right. Oh, I got one more definition. Oh, yes.
Yeah, so. Right, when you wrote that, I was just thinking about how this is a property that's really nice when we're dealing with these class groups. Is there any larger family of dedicated domains for which this is true than rings of alpha rectangles? That's those are the only ones I know that have this property.
What, that have infinitely many?
Prime ideals in each class, or even, I guess, yeah.
There are actually some interesting theorems by Claiborne and some others about how you can distribute primes. But yes, certainly beyond rings of algebraic integers there. In fact, you can basically, you don't have complete freedom, but you can basically make the Dedekind domain be pretty well behaved, and you can make them be pretty badly behaved as well with respect to the prime distributions.
I just need to say, is there any class that we would be familiar with which this is true other than rings of alpha?
Yes, polynomials are rings of algebra. So polynomial rings aren't Dedekind anymore, right? If you take a polynomial ring of a ring of algebra, it becomes a Kroll domain, which is a higher dimensional. But it turns out that and they have something a little bit more general than this, but actually what happens in Kroll domains, or in polynomial rings, I should say, is that primes are always distributed equally among the classes. Okay, so I've got one more thing to do, and that is and let's say an atomic domain, but you can generalize this. We define the elasticity of R, I'll call rho R, via we define the elasticity of the ring to be the supremum of n over m, where you have a factorization of length n into irreducible, the factorization of length m. So, for example, if you look at the ring Z adjoint square root negative 15, we actually have 81. Remember. We showed the deep irreducible factorizations earlier in this semester, right? Notice that So the elasticity of this ring is at least 2. Right? So it sort of measures how wonky, that's a very precise word, how big the ratio between various lengths of factorizations, right? Here, y'all. Elasticity is 1, assuming that R is atomic, the elasticity of the domain is 1, if and only if it's an extra. Because that means that all factorizations, elasticity 1 means that all factorizations have the same, right? And of course, so intuitively, the bigger the elasticity, the crazier you can make the factorization, right? So now that we've defined all this, let me give you a theorem that I'm kind of a big fan of. I think proof might be a little bit different. This is originally due to Valencia. I'll show you the paper actually. Here. Valencia. But R. The all right, with class group G. Then rho of R is 1 if the order of class group is 1. And what does it mean for the order of the class group to be 1? It means that, in fact, it means it's UFT, right? And if not, then you get, this is the Davenport constant of class divided by 2, which, let me point out, less than or equal to for G over 2. If the order of G is 2. Let's go back to this example here. For this example right here, and although we didn't prove this hardcore earlier, we did give a heuristic kind of argument. This is true. Z4 is cyclic, right? And so the Davenport constant, the class group here is 4, right? And so by Valencia's formula, 4 divided by 2 is 2. So this has to have elasticity 2. This is in fact an equality, and this actually gives an example. So not only is the elasticity, and in fact this proof will show that not only is the elasticity of these rings equal to this number, but the elasticity is actually attained, right? Because notice that the elasticity of R is a supremum, so there's no guarantee that there will be an element in there that actually attains that supremum. But for this, it's true. And let me show you, just kind of for amusement here. Here's a historical note on this. Valencia actually only did part of this theorem, but he did the hardest part. He did the hard part of the equality. Narkevich actually did a follow-up paper here that got the complete case, actually. So I guess, Colin, you can see this too, right? This is
we can see it.
Elasticity factorization number fields. Anything scary about this paper? This is one of my favorite amusements here. So this period journal of number theory in 1990. That's right. It was received November 1980. Period. When I first saw this paper, I forget whether I was a graduate student or a young professor, this scared me to death. However, I've been an editor long enough to know that when you look at something like that, it's not clear where the thing lies. So anyway, but it's a great paper, even if it did take many years to get out. Okay. Yeah, and I think actually, I had some dean one time who was complaining about why do people not publish too much, and I showed that paper to them. So, so it makes for a good weapon too, if you ever end up in that situation.
Is the Arcadic paper that follows this one, the one that's like a page and a half, and it just
Yeah.
rolls like the other?
Yeah, it's a short paper. I mean, you know, in defense of that,
I'm not saying, but
they
it's just like
should,
grab.
it should have
no
been caught in the
easy.
original
I'm not
paper.
saying there's anything wrong with it, I'm just like.
Yeah. I have seen that. I have literally seen papers where somewhere in the literature, you will have A implies B. And somewhere else in the literature, you'll have B implies C. And then somewhere over here in the literature, C implies A. And somebody writes a paper, the following are equivalent, A, B, and C. People try to do that kind of thing sometimes. This wasn't quite as like that. But okay, so let's prove this. Let's prove this theorem. I want to use one more kind of sample, and then that'll be that. So for this proof, exercise. The case of G equals 1 is pretty straightforward, so I did go ahead and see if you can figure that one out. So we assume in order to is bigger than 1, and we'll assume I'm going to call the Davenport constant of G. I'm going to call it R. So, so let me work in the class group here. So suppose I have this, a 0 sequence of maximum. You have to remember the Davenport constant of my class group is R, so that means there must be a 0 sequence of length R for which there is no proper subsequence. That's a 0 sequence. What this means is choose primes, EI and I spy, and QI and minus I spy. This is actually, this step right here is a little bit subtle, but it is certainly taking advantage of the fact that we have a ring of algebraic integers, so I have multiple primes in every class, because some of these classes may double up. And to your question earlier, Jared, if you have something that is one of the more general things where you have this, you have infinitely many primes in every class, and you can do this. Or generally, this is a property of rings of integers we're using here. Notice that P1, P2 up to PR this is alpha, and well, let's do this Q1, Q2, QR, beta, and alpha and beta are irreducible. Right? And let me quickly sort of describe alpha. If you could break alpha down into smaller principles, those smaller principles must be subproducts of this. But see, we picked this so that there is no zero subsequence. So there's no smaller principle. This is the key here. Using this maximal length Davenport constant here guarantees that these crazy things are irreducible. Now, check this out. And this is actually, so far, this is very reminiscent of the approach that Zach took in that HFD paper. Also, if you look at PI, QI, gamma I, and gamma I in this as well, by the same argument, P and Q are in inverse classes, so that's principal and irreducible. So what we have is alpha beta with you in the unit R. Right, just by comparing the ideal class factor, the prime ideal factorization. Therefore, rho of R. So I've got a factorization of length R that's equal to a factorization of length 2. That means that the elasticity must be at least R over 2. Which is what I mean by both. So that's one part of the argument that I have with the elasticity needs to be at least VG over 2. How about the other direction, or the other part of the inequality? Well, this is the slightly tougher part of the argument, I think, but it's not too bad. So let's say now suppose get the other part of the inequality that we have alpha 1, alpha 2, alpha n. So these are irreducible factorizations here. Now, I'm going to have to do this kind of tedious notation here, but I only have to do it for the alpha side. So we'll say that alpha I is P11. No, that's not that. I want PI. So suppose that each alpha I can be written this way. And notice that each TI, which is the number of factors here, must be less than or equal to the Davenport constant. Right, because if this exceeds the Davenport constant, that must mean that there's a proper zero subsequence, right? Which means it's a factor. Right, that's this here, of course, follows from the irreducibility. So if we notice that alpha 1, alpha 2, alpha n treated as an ideal is actually P11, P12, P1, P21, P22, P2, all the way up to P M1, P12, P. Right? And of course, this is also equal to beta one, beta two, beta. Now, I've got length n over here. And so you might want to ask yourself, okay, if I redo this in terms of the betas, that involves shuffling some of these prime ideals, right? So let me point this out. If I shuffle this prime factorization has to be reshuffled into this. So let me ask you this. Of course, we're assuming that all these PIs are non-principal primes, right? Because let me point out that, of course, if I probably should have said this at the beginning, but if say alpha one is prime, then that means that it must be one of the betas up to associates. And I'll just cancel those. And that actually makes the elasticity that improves down a bit. So if I reshuffle to the longest possible factorization into elements, bring principal out of this occurs theoretically maximally when each beta I is a product of two the right? That's the way to make the principal ideal the longest possible is if you compare that off, right? If each PI had a pair that made it sort of a companion, a single companion that made it principal. And that observation actually gives us enough bound in the following sense. So, M, that is the number of factors that I can make over here, is less than or equal to T1 plus T2 plus Tn over 2. So the number of factors that I can create over here is the total number of these primes divided by 2. No more than that. No more. Everybody okay with that? So long as I can make it. And so this means that M over N is less than or equal to T1 plus T2 plus Tn over 2N. Now these, each Ti is no more than the Davenport constant. So this is upper bounded by N times R, which is less than or equal to R over 2. So in other words, every one of these ratios is less than or equal to dg over 2. And so that means that dg over 2 is actually greater than or equal to. So in particular, combining these two, so there is a very important connection for Davenport constants. Yes.
Can you talk about assuming that none of the alphas and betas are primes? You mean like, in the sense that we can assume that none of them are without loss of generality because we could divide them out and that would only increase the elasticity because we're looking. And so we can do it without loss of generality.
Right.
Right.
Yeah, that's right.
Are you aware of any, so we're talking about Dedekind domains, we have unique factorization of primes.
Mhm.
Is there any analog in item pro dimension where products of primes have to be of equal length, but not necessarily sort of like UFD versus HFD.
When you're talking about primes, do you mean principal primes or do you mean like just general?
Prime ideals.
Okay, so the question is, you have what product of prime ideals always having equal length?
Yeah. The pro dimension one that would.
Yeah, I'm not sure. Why don't you bring that up later? And I'm not sure off the top of my head.
Because, yeah, it occurs to me that this proof would work. Just
Right.
based on equal length.
Right. Good. Other questions? Okay, I want to give you one kind of, sort of one to grow on here. Here's a final kind of hazards. Of course, one hazard for example, Davenport constant, and you kind of bring this up in your question, is this is a really, I really think it's pretty big. But we had to throw a bunch of assumptions at it, right? I mean, that's always the way it is, less assumptions, less pretty, in a certain sense. So there's that limitation, but there's also dangerous hazards of monoids too. So for example, if you had monoid, the Graham's monoid, which is now sort of effectively powered, then this is atomic, not ACCP. Then if you look at this is also atomic, not ACCP. Monoids are actually a very great tool. If you like integral domains, they're kind of a good first pass tool. The problem is, in a certain sense, it's easier to build monoids because you don't have that pesky addition to worry about, right? It's just one binary operation. You can kind of do, you got more freedom in a certain sense. So for example, this is a unique factorization monoid. There is one irreducible element here, one, right? And everything is uniquely a sum of ones, right? 10 is 10 ones and so forth, so on. If you look at F, X, and 0, this is Fx, which is in UFD. Nice. It's preserved just like it was in the Graham's model. Yep. Let's look at this one. Remember, my irreducibles here were 2 and 3. By the way, this is called a numerical monoid. It's just a submonoid of the natural numbers that, well, yes, it's a submonoid of the natural numbers. It's only missing finitely many natural numbers in this case. And notice it's generated by the elements 2 and 3. Right? You got 2 and 3 together. This is not a unique factorization monoid. Because you have that situation. And in fact, not only is it not unique factorization, it's not a hack factorial monoid either. Because the factorization on the left is like 3 and the one on the right. Agree? But it does have something that was originally called the other half factorial problem. That is although this terminology started out as a joke and it is sort of recently been retired. This is the other half. Let me point something out that's interesting about this, because there are two assumptions for UFD, right? Basically, after you know it's atomic, you have any two different factorizations at the same length, irreducible factorizations at the same length are equal, and they're equal, right? So first thing, same length, second thing, they pair off. Right? What if they only pair off, but they're not equal? So that is to say, this has the following property. If x1 plus x2 plus xk equals y1 plus y2 plus yk, then up to ordering xi equals y. So in other words, any two factorizations of the same length are the same. This actually has its property. There are factorizations that are different that are of different length, but if you have two factorizations of the same length, they're the same. And I feel like a complete tool for actually proving this to you because it's quite silly, but I will do it. In this particular monoid, there are two irreducibles, 2 and 3. So maybe I've got 2a plus 3b equals 2c plus 3d. All right. And I assume these have the same length. So I have a plus b equals c plus d. Right? We're here, of course, a, b, c, d are not integers, but they're in natural numbers, union of 0. Well, multiply this by 2 and subtract, and please let none of my linear algebra students walk in here now. Times 2, subtract, and I get b is equal to b, right? And once you've got b equals d, then this gives that a equals c, right? And so a equals c and b equals d, so the factorizations are the same. In fact, it turns out that if you have any two generated numerical monoid, it has this property. That you may have factorizations of different length, but if they're the same length, they have to be the same. Right? Now, what about does that have this property? The answer is no. And here's the theorem. I believe it's 2011. If R is that is, it has this property that factorizations might have different lengths, but if you have two factorizations of the same length, then they're the same. Let me see correctly. If R is atomic, then R is an OH. You can only do R is a U. And this should tell you that monoids are easier to make in the following sense. This is a monoid that has the OHFN property, right? That is the equaling factorization the same. But it is clearly not, does not have unique factorization. If you take this property that equaling factorizations have to be the same, and you thrust it upon an atomic domain, then you also force there to be no factorizations of non-equal length, which is kind of interesting, actually. It turns out actually that atomic is important in this because you can actually create integral domains that have exactly this as the atomic factorization structure. But this theorem tells you that any such domain actually has to be non, or it can't exist. So anyway, so that is my indulgence. Thank you for indulging me. And that's it. Any questions? Yes, sir.
It's not really a question, so like, I just remember in Algebra 1, when you defined what UFD was, you defined it as having the OHFD property and the UFD property. And then right after that, you defined it as just having the OHFD property. And I remember everybody in the class was like confounded because we were like, well, this definition is just like strictly weaker than the other one. So why do we have both?
Yeah.
But it's like, well, in this case, they're different, but
Yeah, that's right. They're different in this case. And yeah, and the fact that this is equivalent is not true. It's not a triviality. So, any other questions, comments? Well, I should be finished up with your homework today. If you're lagging behind, just try to get me stuff as soon as you can, because I got to get grades in early next week. I've enjoyed having you all. Once my student, always my student. So let me know if I can help you in the future. Have a great break, y'all. Well deserved. I'm gonna go comatose in front of Netflix for 3 days after I'm done. See y'all.